So today we're going to look at the intersection of kinetics, equilibrium, and economics with two application scenarios of these two industrial processes. Now, you don't have to know all the details of these processes specifically, but they're just really good examples, and so you should be able to apply this to other processes. So we've already talked about kinetics, we've talked about equilibrium. Your basic tenet of economics that you need to know for this is time is money. Okay, so we're going to talk about the Haber process to start with. So here's Mr. Haber, and he developed a way of producing ammonia. So ammonia is very largely produced, about 120 million tons each year, and about 80% of it is used to make fertilizers. Now, it's also used in the production of plastics, refrigerants, and even some explosives. But its role as a fertilizer is why this has such significance. Much of Europe's raw materials for fertilizers that had nitrogen in them came from South America. And as World War I got off the ground, there was a blockade that kept the supply chains for both sides really from getting their raw materials. And Fritz Haber, who was German, figured out this process. Ironically, he was also Jewish, and we'll talk some about that as we go through. But anyway, so he figured this out. And it's taking nitrogen from the air and hydrogen from water to make ammonia. So it's exothermic, and delta H is negative. So we need to think about this in terms of equilibrium. So if we increase the temperature, exothermic, that would shift the reaction to the left, which is not what we want. We want to do things that would shift it to the right. So we would want to decrease the temperature. We would, in terms of pressure and volume, we've got 4 moles versus 2 moles. So if we increase the pressure, that'll shift us to the right. So we want a higher pressure. Okay, well, what happens if we add some more hydrogen? Well, that would shift it towards the right, so that would be good. That's not where it should have popped up. Adding a catalyst, though, will not change the equilibrium position. So those got out of order. Okay, so again, a catalyst will lower the activation energy, but it changes it for the forward and the reverse reaction, so it really doesn't change the position of equilibrium. So here's the optimum conditions. First off, in terms of concentration, we use the appropriate mole ratio of nitrogen to hydrogen, and we remove the ammonia as it forms. So if we're pulling the product out, we're removing it, then that continually shifts it to the right. In terms of pressure, well, I've got 4 moles of gas versus 2 moles of gas. So we're going to use a high pressure. 200 atmospheres is what is used. You don't have to know that specific number, but know that we want a high pressure to shift it right. In terms of temperature, so this is exothermic, you would expect to use a low temperature. However, at low temperature makes it uneconomically slow. Remember that whole time is money part. So we're going to use our kinetics and know that we need a higher temperature for a quicker reaction. And so we use what they call a moderate temperature, 450 degrees Celsius. Now, a catalyst doesn't change equilibrium. It doesn't change the yield, but it does speed up the reaction. So we use a catalyst, and that is finely powdered iron in this case. Okay, so the rest of the story with Haber, oh, by the way, even with these optimized conditions, yield's only about 15%, so this is not a super economical process. So Mr. Haber, there we go. He dealt a lot with gases. He also came up with a really good insecticide called Zyklon A. And then his work on gases kind of petered out. He fled Germany as World War II approached, and it wasn't so popular to be a Jew. Zyklon B, though, they took his research on Zyklon A, formed Zyklon B, and that was what was used in the gas chamber. So some very severe irony there. Okay. Our other process, our example is the contact process, which is the production of sulfuric acid. This is the most produced industrial chemical in the world. Okay, it's used in production of all sorts of things: fertilizers, detergents, dyes, explosives, guns, or not guns, that says plastics, and drugs, and many other chemical industries. Okay, the name of it is not named for Mr. Contact. It's named that the molecules of the gases of oxygen and sulfur dioxide react in contact with a catalyst, V2O5. So there's actually 3 steps here. There's the combustion of sulfur to form sulfur dioxide, the oxidation of that sulfur dioxide to form sulfur trioxide, and then we react the sulfur trioxide with liquid sulfuric acid to form ultimately more sulfuric acid. Okay, this right here is the slow step, that second step. Okay, and it's also exothermic. So in terms of pressure, we've got 3 moles of gas versus 2 moles of gas, so we're going to use a high pressure. In terms of temperature, it's exothermic, so again, we would want a low temperature, but then we deal with the rate of the reaction as well, so we use a moderate temperature. And we also use a catalyst. It increases the rate of the reaction. It does not shift equilibrium, and we use V2O5 here.